Yeah, I would probably say just try to speak into the mic. I can also adjust it if it's like not. It's mostly for the recording. Right. Ron, should we put it up? It's not for the. So please welcome Evante.
Hi, my name is Evante. I'm from the Bay Area, close to Oakland. So I don't know most of you. So I've been doing Purescript for a couple years professionally, a bit longer than that, just personally. I think my first major compiler upgrade version was 0.7. That was back when you had a lot of, like you could do pattern matching on arrays of indeterminate length, and you never really use this. But it's one of the things I miss. Anyway, so I'm going to be talking about Metaprogramming Purescript, almost arbitrary different values. I'll start with looking at the motivation for this library that I wrote, and then we'll go into a little bit of how generics ref works in Purescript and then the row list, and combining the two to sort of create this library. So the motivation, suppose that you're writing some tests for your code base, and at some point you want to compare two things for quality, but the problem with a lot of code bases is that the data types you're working with can get nested really quickly, and they get fairly complicated. And so sometimes when you're running the tests and something goes wrong, it kind of sucks. So for example, can you guys see this? Okay, sorry, it's my editor thing.
Y'all can come closer too. Like we have these to sit on, and there's more of these. We can move further.
I can try to explain what's going on. So basically, it's...
You can invert the colors. You can invert the colors in the OS.
Can you show me how to do that? I don't remember how to do that.
I mean, that makes sense.
Okay, so basically it's a small bit of code that you get some unknown answer from a mock process, and you have a known answer that you know is supposed to be equal to whatever this process does. And this last line is basically unknown answer should equal known answer. And if that goes wrong, okay, so this is my terminal theme, and it's also dark, so sorry about that. But basically, there's maybe 20 lines of unformatted red text. It just says, a bunch of JSON, and then somewhere in the middle of the screen there's a not equal sign, and then there's a bunch of JSON. And so looking through this can really suck, right? And if you want to drill down into the bits that actually are witnesses to inequality, that can also suck if you're writing this thing manually, right? So you can have this diff function that takes in two complicated data types and does some effectful action in some monad effect or whatever. And you can start writing this as first you check that the array lengths are the same, and if they're not, then you zip them, you traverse through you can compare each element and make sure that the fields are the same, and if not, then you console error. And if they are, then you just keep going through, and this can like blow up in the size of the complexity of the data type. So one of the things to notice is that there's nothing really too clever happening in the diff function. It's pretty formulaic, so maybe we can generate this automatically. So I broke it down to roughly 3 major cases. The first is the atomic types, which I'll get into what those are in a bit. Other types are built-in types of kind k to type for some k. So I'm thinking of records, which are row type to type, or arrays, which are type to type, right? And then user-defined types, which are ADTs. And so what are atomic types? String, number, char, etc., built-ins like that. There's void and unit. There's also support for if n is a new type of A and A is atomic, then you can consider n as atomic too. And so, well, how do you compare atomic types? Say if you're diffing a string and a string, well, there are a couple ways to do that. I don't really want to commit to a certain way. If you diff a number and a number, you'll get another number, like 5 minus 3 is 2. So we'll just leave that up to the user. So we'll take in a callback of type, it takes in 2 atomic types, and then gives back some effectful thing, and some m, might be a monad, might be an applicative, not really sure. So for composite types, this is where things get interesting. So basically we want to pass the callback through the sums and products. And like I said earlier, we're interested in ADTs and records because those are where generics like rowless machining comes in. So this is where metaprogramming comes in. So what is metaprogramming? There's some examples. So if you do Haskell, which I'm sure most of you do, I think one of the best examples is this make lenses user sort of thing. So you don't have to write out that boilerplate for your lenses. Rust has macros like type-safe formatting. My favorite prime is 2, something like that. List macros. This is really interesting, but I don't know about it. So there's this language called Hackett. And from what I understand, the type system is based off a paper called Type Systems and Macros. And I know that ADT support in Hackett is defined as a macro, which is pretty crazy. And in Purescript, you have generics, row list, and type classes. Okay, so generics in Purescript are pretty easy to work with, I think. They're solved by the compiler. So the code that you write usually looks like derive instance generic, which is of type generic user underscore, right? And so they're solved by the compiler, but what is the actual solution? What is that underscore? If you look through the docs, it's maybe not quite clear what everything gets represented as, but we can always talk to the compiler. That's one of the greatest things about using a strongly typed language. So what we can do is look at this function from data.generic.rep. It's called from, and the type is very simple. If A has a generic representation, then it gives you the representation from the actual value. And so we can use stuff like type folds, right? So we're calling from, this from right here in data.generic.rep on some user example, and then we put in a type fold, and the compiler tells us what the representation is. The representation of this type is constructor, user, argument, blah, blah, blah. And so you can do this trick for pretty much any type if you want to see how it's represented. So broadly, if you're working with generics, you want to define a class where the methods work on the representation instead of the actual values themselves. And then you transform the type to the representation. You do work on the representation, then you transform it back. So that's actually really simple. Row list, I think, is a bit more complicated because it's a lot more type machinery instead of value level machinery. And in Purescript, row list is the only way to give instances to records that depend on the record structure. So you could give like an instance for, I don't know, say show, that always gives back the string, the empty string, for example. That'll work on records, right? Because you're not actually depending on the record structure. So if you want to actually do anything interesting, you pretty much have to use row list. So the compiler has special knowledge of the row list stuff. And I think the best way to explain how row list works is you can think of records as heterogeneous association lists, right? An association list is just a list of tuples where the first element is a string and the second one is a value. Heterogeneous because records aren't required to all have the same value. And so if you can think of records as association lists, then how do you run a list? Well, you're either going to fold it or you're going to pattern match. Those are like the bread and butter of working with lists, right? And in either case, you have to give two code paths. One, which tells the program what to do in the case of an empty list, and the other one in the case of a non-empty list, right? And then basically it traverses through the list and runs this until the list is all consumed, right? So we can do a similar approach when writing instances for records. But because instance writing is happening at a different level than just like writing functions, you can actually have non-exhaustive patterns. And as a result, if you call it on a pattern that isn't covered by the instance, you'll get a compile type error instead of runtime error, right? So like, I think the clearest case of this is in Haskell, there's head in the prelude, which takes in a list of any type, A, and then gives back an A, right? But we all know that that type is a lie, right? Because if you give it the empty list, it errors out, it crashes, it yells at you. So because we're working on a different level, we can use non-exhaustive patterns. And so I think this merits looking at an example. And again, sorry for my editor. So basically, we define a class called RL to list. RL you can think of as row list. And it has three parameters. RL is a row list. It takes in a row, which is an actual row of types, which is separate from a record, right? A record takes in a row of types and gives you back a type. And then some A, which is a type. And we need this A because we can't really work with heterogeneous lists without doing some extra work, like using existential types or something, but it gets a bit hairy. So the single method in this class, we'll call it RL to list. It takes in a proxy of your row list, which, remember, is of kind row list, not of kind type. So that means that values of kind row list don't exist, right? Because runtime values always have to have a kind type. It takes in a record that has this row, this parameterized by this row, and then it spits out a list, an association list, right? A list of tuples string A. And so, very simple case. I always call it the basis case because for me, personally, I think of row list stuff is akin to proof by induction. And so the basis case is basically where your row is empty. You don't have any keys, any values, anything inside. And the sensible thing to do is to spit out an empty list because, well, we don't actually have our hands on any values of type A, so we can't give you a value of type A, right? And the hairy part comes in the inductive case, which I call inductive. I'll try my best to explain this, but I've added type annotations for pretty much everything, so hopefully that helps. So ignoring the constraints on the instance, the actual right-hand side of the definition, you'll see it's just a list cons. So we take some head and then we cons it to some tail, right? And this RL to list ignores its first argument. Why is that? Well, because the first argument is a proxy, right? And we already have all the information we need from that proxy in the constraints, right? And we have the rec, which is the actual record. So looking at the constraints, we have to work with a symbol. So we have this is symbol class on K, which you can think of as a key. We state that the row tail lacks this key, right? Which makes sense because we want to do some work on this new key that showed up. And we also want to assert that the row that we're looking at is composed of this key along with some type A, or some value type A, cons onto the front of the row tail. And then the last constraint basically is the, what I think of as the inductive hypothesis, which says that you've already done this work for the tail of the row list, and so that instance is already somewhere, right? And so basically you create this head type, or a head value, which is a tuple string and a value type A. And then the tail you get by deleting the part of the record that holds, that's at that key. And then the tail you get by this sort of recursive call to the method. And then you can basically you do work with that and you put it all together, like in inductive proof, and that's pretty much it. So, putting it all together, basically when we look at value of type whatever, we traverse through it carrying this callback that we looked at before. We also carry a list of indices, which is similar to a call stack. So in case you get these like giant errors, it can tell you like, oh, it's at the third position of this array inside, I don't know, maybe, where it was a just, and then inside that was another array, blah, blah, blah. And then eventually you get to, oh, like 1 is not equal to 2. Okay. So on products, you go into each factor, and you basically call this diffing recursively. On sums, you have to check that each sum end is the same. You have the same constructor, basically. So that's like making sure that adjust is the same as adjust and not a nothing. And unsupported, in quotes, FFI and functions. If you want to do these, you need to handwrite instances, sort of like what we looked at in an earlier slide, where you have to manually write out this different function. Yeah, so here's a very short list of references. There's this type systems as macros, which I mentioned I didn't look into that much, but looks really interesting. And the library, which I just published yesterday, I call it Purescript Diffie. It's on my GitLab. I'll probably mirror it on GitHub later. And yeah, so basically it lets you get rid of all this manual diffing. All you have to do is basically define your data type, derive generic, and then derive these sort of generic. You give another instance for this generic diffie class, and then you can use that in your tests. And the tests right now are a bit of a mess because I'm going through and refactoring, adding stuff, taking stuff out, like some things are complicated. But I think it gives an okay overview of how to use it. So yeah.
Are there any? Oh, sorry. Go ahead. Yeah, just wanted to give you a sec to swallow that water. So this is able to tell you, deep in this array inside of maybe inside so on, there's a difference between these two. Is it able to also keep track of multiple differences, or is it kind of tell you, here's the first one, and then once you change that, here's the next one?
Okay. All right. So that's a really good question. And
Could you repeat the question?
yeah, the question was basically, does it stop at the first error or the first difference, or can you keep going? And I sort of brushed over that in an earlier slide. Let's see, did I? Yeah, I'm going past it. Hold on. Yeah, I really blew it because it was very small. So here I sort of handling it differently. The callback is atomic A to A to M unit is a callback for some M. So the way that I've implemented this is that M just has to be an applicative. So you can write your own applicatives. In particular, you could use something like I think it's called V, right, from data.validation or whatever, which supports collecting errors and not stopping at the first one, which is what you would have if you have like this monadic sort of error strategy thing. Originally I did have a monad constraint, but then I realized I could rewrite all my do statements with applicative do statements, and then that made it a lot easier. Or just with sequence or traverse or whatever. So yeah, in the test file I have a couple different M's. Like there's in effect M, which is for printing console as I have a writer. That basically collects whatever the differences are. So yeah, it supports basically collecting all the errors. It really depends on what M you're using. Phil?
You have an array instance on student, right?
Yeah.
Does it do like, I think, what does it do? Like, if you insert in front, does it like tell you that it inserts at the front, or does it like give you the model?
Okay, so that's an implementation question, and I haven't actually looked at the code base for like 2 or 3 months. So there is an array instance. I don't remember what I'm doing in it. Yeah, that's the best answer.
I assume it does sometimes.
It does what?
Sometimes.
Yeah. So what's weird is that some things that are some types don't derive generic. Like from what I remember, the list type, for example, in data.list is an ADT, so it would fall under like a user-defined data type, but I don't think it derives generic. So for some things, I had to write instances for data like popular data types that already exist. But yeah, you can write your own sums, and I don't think I have a test case for that. I think I just have a test case for a user-defined record new type. But when you look at sums, basically you check that they're the same constructor, and if they're not, then that calls a different callback. So the callback is actually a bit more complicated. There's basically one callback for each type of error that you could run into, and that would be one of them where some branches are actually different because you can't really compare those, right? So yeah.
Is it using like equality from equal like type class, or is it just doing it on its own? Because you might have like a different distance of equality, like when you're making a new type, you might have like a custom like.
Yeah. So the question was that if it depends on the equality type class from what is it, data.eq, I think? Yeah. So personally, philosophically, I really hate it when libraries depend on eq. I think they should always expose a, say you expose a function called diff, and then it takes like eq a to bool or whatever, or I don't know, to a to a. I always prefer when libraries expose a diff by, which basically takes an explicit dictionary, right? So some function of type a to bool, and then you can define a diff, which is diff by eq, right? Which is the normal data.eq. So no, it really should not depend. I don't think it depends on data.e. From what I remember, I think I was pretty careful not to do that. That's also part of leaving up what to actually do with these types to the user. So you could, I was actually fixing some bugs in my test folder. I noticed that I was not even checking for quality, so when I would run my test, it would say stuff like, unit is not equal to unit. Like, wait, that's not right. This unit is always equal to unit. And that was because I didn't do the checking for quality myself. No more questions? Thanks.